Ladies and gentlemen, it is indeed a pleasure to present our next speaker. Today, in my opinion, we have with us a true hero of modern science. He's really a modern-day Galileo. Like Galileo, he's used the astronomical telescope to overturn an antiquated cosmology. Like Galileo, the high priests of orthodoxy have refused to look at his results. Like Galileo, he's been denied the right to publish his results. Like Galileo, he's been punished, in this case by being denied access to the large telescopes he used to make his discoveries. And most important of all, like Galileo, he's going to have the last laugh. Yes. It is a sincere honor to present to you the man who has discovered the true meaning of redshift, and by doing so has single-handedly opened the door to the 21st century in astronomy and cosmology. He's the author of the Atlas of Peculiar Galaxies that are famous worldwide. Join me in welcoming Halton Arp.
As I mentioned Friday night, the important thing, I think, is to see the observations, to communicate the evidence so that all of you can, everyone has to make up their own mind on this. But as I go through this, you'll see there are certain obvious patterns that are developing, and in order to predict what the new observations will show, and in order to understand what they mean, we'll start talking about the creation of galaxies, the creation of matter, its effect on relativity, and its implications for our understanding of the universe. But I'd like to start with the first transparency. About in the early 1950s, the radio telescopes started observing the sky, and they found sources of radio, pairs, spots of radio emission on the sky. I remember sitting in the Caltech symposia room and scientists saying, well, they're paired across galaxies, but you should not jump to the conclusions that they're associated with galaxies. Eventually, of course, they saw these thin connections going from the central galaxy out to the radio lobes on either side. Now, I know this is a beautiful picture. This is a VLA picture, or the best available presently. But I think the two important things you should draw from this first slide is the fact that this material is actually being ejected. That's about the only way you could get this kind of a configuration. And secondly, is that it's coming, this large amount of material is coming from this very small active spot. This is Cygnus A. And so I think we start out with the knowledge that galaxies, unlike assumed in the early days, are not quiescent star piles just moving around, but they actually have very active centers, mysterious active centers. The next step was the Atlas of Peculiar Galaxies. After it was finished in 1966, I looked, the major result for me was that these peculiar galaxies, which were featured in that atlas, 333 of them, they were disturbed in the center. They looked as though they were exploding or ejecting. And so the obvious thing to do is to look around to see whether there are any of these radio sources in the vicinity. I was also helped because a friend of mine in Argentina said, gee, Chip, there are a lot of radio sources around those galaxies. And and so when I looked at them, I saw, in fact, that they were paired across these exploding galaxies. That made a lot of sense. They were being ejected, and in the process of ejection, the galaxies were being disturbed. So the chances of that association being accidental was only about 1 in a million. And I immediately, in 1967, 1968, turned it around and said, let's look for radio spots or pairs on the sky and see whether there's a galaxy between them. And this is one of the objects that turned up, where there's two very strong radio sources, those small dots there. They are the only ones in the area. They form an obvious pair. And then when you look for the brightest galaxy in the area, you see that's IC 1767 falls directly between them. Now, at that time, all I knew was that those were quasars, because some of these radio spots then became associated with optical objects. They look like stars, but as you know, quasars have very high redshifts. The lines are shifted to the red, which is usually interpreted as, or up to then had been interpreted as meaning they were receding from us with high velocities. So after this was found, these quasars were measured and confirmed as quasars. And you see an amazing thing here. The redshifts are written there, 0.616 and 0.669. Now, quasars come in redshifts between 1/10, and now they're up to 4 or 5. And so the chance of them being that close together in redshift was very, very small. So that meant that the pair was associated and that they were associated with the central galaxy, and the conclusion was that they were ejected. Now, these kinds of objects, this was published in the Armenian journal because it was obviously not going to get into the Astrophysical Journal. And later it was published in the Astrophysical Journal, but not much attention was paid to it. But nevertheless, this kind of material started piling up until about 1995, when the German Rosat X-ray satellite went up and started observing X-ray sources. And there are 3 primary X-ray sources which you would naturally observe. One are disturbed galaxies, Seyfert galaxies, which I'll come to in a minute. The other is quasars. They're compact objects emitting a lot of radio material, but even more X-ray emission. So they're very bright objects and something that the X-ray telescope would look at. And at the end, I'll talk about clusters of galaxies. Surprisingly, these clusters of galaxies are emitting huge amounts of X-rays. So when in 1995, this Rosat X-ray telescope was pointed at this Seyfert galaxy, NGC 4258, it was clear, it was already known it was a strong X-ray source, and you can see these isophotes in the center representing all the X-ray material, the emission that's coming out of the center. And also, it was known optically that this galaxy was ejecting. It had been ejecting hydrogen clouds, continuum radio emission, and so forth. You could see it in the optical. There were anomalous arms coming out of the center, and so forth. So already we knew that this was a very active galaxy. But the surprise came when you saw those 2 spots, and Amy showed this yesterday, these 2 spots of concentrations of X-ray right across the center of this galaxy. And it was even the conventional person who did this observation said it looks like they're ejected. And of course there were 2 stars, 2 stellar appearing objects at the center of each one of these X-ray emissions. And the question was, how could we confirm them as quasars? Because it was obvious that they were quasars, but nobody wanted to do it. And finally, Margaret Burbidge came along, and rather heroically, I think, went to the Lick 3-meter telescope on Mount Hamilton, and on a poor night over the lights of San Jose, got the redshifts of these 2 quasars. And the redshifts are interesting because they come out to be 6/10 and 4/10. And the implication is that one of them is coming toward us with a 10th C, and the other one's going away from us with a 10th C. And that's really important, because we'll see later that if you're going to make these quasars, they're going to have to start coming out with very high velocities, near the velocity of light, because they're low mass material, and then they're going to have to slow down. But here, when we have these redshifts now, we can actually measure the velocities of the ejections, and they're in the range of 5 or 10,000 kilometers per second, not 300,000 kilometers per second like the velocity of light. So immediately this result came out. Incidentally, this is my picture from the 4-meter telescope at Kitt Peak, and I had been in the years before looking for just these kind of objects around it. But when the X-ray telescopes came along, they picked out the quasars very, very well. And you'll see this now with sort of a Rosetta Stone making progress in this field. And the thing we did next, a colleague joined me from the Max Planck Extraterrestrial, and we looked at all the Seyferts. Because the Seyferts were such strong X-ray sources, we were able to get almost a complete sample of the brightest Seyferts from 8th apparent magnitude to about 12.9. And we could, the X-ray sources were then automatically reduced by the reduction program so that they were listed. The point source X-ray sources in the vicinity of these Seyferts were listed. And what you see here is these points going up and to the right are excess X-ray sources around the Seyferts. The dashed line indicates the control fields, fields away from the Seyfert galaxies. So we could see right from here that this was an excess of point X-ray sources around these active Seyfert galaxies. You don't need to be a rocket scientist to know that these were quasars. And everybody knew they were quasars. But the question, of course, was, since they didn't have redshifts, you could sort of ignore it. The statistics that we did on this was a 7.5 sigma result, i.e., the chance of this being an accident would be 1 in over 10 million. So that this was what the scientists, the conventional people say they really wanted, was a statistical proof with a large sample of objects showing that the quasars were associated with these nearby galaxies. These high redshift quasars were associated with nearby galaxies. But when the result was obtained and published, of course, no one would again pay attention to it. So we started this difficult procedure of picking out these sources and trying to get the spectra and getting the redshift of these quasars. And I'll show you a few examples of the things we got. Here's a Seyfert 1. This shows a lot, just this one object. Here's a Seyfert 1, a very bright one, known. A redshift, very low redshift, 0.007. And on either side is a quasar, 0.334, and a BL act object, 0.136. That's a special kind of quasar, which the synchrotron of the Bremsstrahlung emission is so strong it wipes out the lines, and it's almost a continuum high energy source. And that'll be interesting. We'll come to that a little bit later. And then when you draw in the minor axis of the galaxy, you see it goes more or less along the line to those two pair. And we will argue later, this is kind of a common sense thing, and that is if a galaxy is going to eject something, it's going to eject it along the path of least resistance, which is out the poles. It's very interesting that in some cases this monster or the machine inside doesn't eject it quite out the poles. It maybe ejects it at an angle or maybe even in a plane. And in that case, sort of all hell breaks loose. You get fragments and nearby quasars and very disrupted galaxies. We'll see a few of those too. This is another one that Margaret Burbidge did across the Seyfert 2639, and you see the pair of quasars, 0.325 and 0.307 redshift. Well, these redshifts are getting so close together that you know they cannot be accidental. And these are, as we'll see later, preferred redshifts. The redshifts, as you notice as we go through, come in a redshift 0.065, 0.30, 0.60, 0.96, 1.41. And they actually fit a formula called Carlson's formula. So all these are characteristics of the association which is repeated again and again. You might say we've been predicting this, and each one of these observations is a confirmation. Another example, and this I thought was really the Rosetta Stone of the group, is NGC 3516, and all the X-ray sources in this area are marked by these points. And now the person who got these redshifts was Yao Quan Chu, who's a Chinese astronomer at the University of Hefei in China. And he did it with a 2-meter Beijing telescope. And we're getting pretty small telescopes now for these somewhat faint objects. But he got all these redshifts. And they were really amazing because you see the nearest redshift to 3516, the one that's closest, is the highest redshift, 2.10. The next one, 1.40. then further out 0.93, 0.69, and 0.33, and finally 0.089. So you have this nice relationship that the quasars, as they proceed out, as they're moving out, as time goes past, as they age, they're dropping in redshift. And the other thing you can see is that they don't drop smoothly in redshift, but they drop in these preferred quantized redshifts. And you can just see 0.30 at 0.33, 2.1 should be 1.95, 1.40, 1.41, etc. They all fit this redshift pattern. Another example, to keep that for just a minute, I want to point out something important. After this was all done, we drew the minor axis I drew the minor axis of 3516, and you see it goes right through the points. This paper was sent by Chu and myself and his Chinese collaborators to Nature magazine as a really important observational discovery paper. And of course, they turned it down without even sending it to a referee. They can recognize bad papers when they see them immediately. And then I sent it to the Astrophysical Journal Letters, and they said, well, I suppose we'll have to publish it, but it's not very important. We'll put it in the main journal because it was just a small letter. And finally, it was published in the main journal of the Astrophysical Journal. But again, not much attention was paid to it. Another example like it came about in an interesting way. I picked up the Astronomy and Astrophysics, the European journal, one day, and I saw this paper titled A Quasar 2.4 arc-seconds away from a dwarf galaxy. And it turned out that there was this quasar at 0.81, you see, next to only 2.4 arc-seconds away. It was practically right together with this galaxy. And they went through a big rigmarole saying that, well, it was only 1 in 1,000 chance of being accidental, but of course it had to be accidental. And I immediately looked in the vicinity. I said, there must be a Seyfert galaxy here. And sure enough, there's 5985 with a redshift of 0.008. Then I looked around in the region, and here are the quasars along that line. Again, they're at the quantized redshift values. And again, when you draw the minor axis through, the minor axis looks as though it's been drawn through the points, but it hasn't been drawn through the points. It's been drawn through the minor axis of the galaxy. And so that did manage to get published. The next example, you should move in a little bit, and this introduces the point that along this line of ejection of these high redshift quasars, there are some companion galaxies. They're drawn by open circles there, and they are more or less the redshift of the central Seyfert, which is 2467, but they're 100, 200 kilometers per second higher. So, and they're along the same line of ejection. What I have interpreted this to mean is that these quasars move out, evolving to lower redshift, and then they can fall back in along that line because they don't have any angular momentum to carry them away. And they develop into companion galaxies, but they're still a little bit younger than the main galaxy. Therefore, they have a slightly higher redshift. And this is important to set up the full transition between the high redshift, mysterious, newly created quasars, and the galaxies that we know all about, because that's the evolutionary development of a galaxy, and that's where galaxies come from. A Swedish astronomer in Pasadena in the 1970s who showed that the companion galaxies, these ones I was just talking about, were distributed uniformly or preferentially along the minor axis. And here I've shown that the quasars are plus or minus 20 degrees from the minor axis, and the companion galaxies are plus or minus 35. This reinforces the conclusion that as the quasars come out along the minor axis, they get out, develop, and then are perturbed slightly, and then when they fall back to form the group, they're a little bit more spread along the minor axis. And this distance out, which was calculated at the time, is a half a megaparsec. And that's just the diameter of groups. That's the diameter of our local group, is a megaparsec. So it looks like the major constituents of the universe are made up of these groups, and this is how the groups form, with a parent galaxy, quasars, and then evolving into companions. This was in 1970s, early 1970s. there's this galaxy that's obviously losing it. I mean, it's coming apart. The arms are coming off and so forth and so on. And there is this quasar, Mark II and Mark 205, connected back by a luminous filament. We're going to a different level of proof here now. Before we had the associations, the pairing, statistical, so forth. But here now we have an actual luminous connection, actual physical connection. But and therefore this stirred a tremendous amount of resistance and animosity and bad criticisms and so forth. This was taken, finally, I discovered it on the 200-inch, and then this was a 4-meter CCD photograph which showed it. And a number of astronomers with large telescopes said that the connection didn't exist. And, well, I mean, so it sat there until last year on the web appeared this next picture, which I was unaware of. Some friends of mine told me about it. And it turns out that there's this amateur in England from the English skies, which are noted for being poor observationally, with a 50-centimeter telescope, half-a-meter telescope, and a CCD has taken this, and the connection shows beautifully. I think that this is should be an enormous embarrassment to the people, the professionals with the large telescope, and an enormous encouragement to the amateurs. And in fact, and I hope there are some amateurs here, because I know the amateurs in Italy and other places are encouraged now to go over this whole group of objects and try to search for more confirmatory examples. But I'm terribly pleased by this. I'm terribly pleased that it came from the amateur community, because they're the ones who really look at the photographs and really think about what it means. And the professionals tend to be specialists and only look at what's predicted by their theories and so forth. So that's one of the latest developments. I might say that this Markarian 205, which I called a quasar, is really sort of a transition between a quasar and a compact galaxy, a compact young AGN, what they call. They've arbitrarily set the limit for a quasar as minus 22.5 magnitudes on the basis of their redshift distance. And this has confused the whole subject enormously, because this then is just on the line between being a quasar and a AGN, luminous galaxy. But I suppose it's also illustrative of this transition, of this evolutionary passage between quasars and galaxies. And the next slide will show you an example of this. This is NGC 1232, a famous SC1 spiral galaxy in the southern hemisphere. And I had worked on that. There's this little galaxy that has a redshift 1/10 the velocity of light. And I would argue it's obviously interacting with this arm and causing a disturbance in this arm right here. This galaxy is obviously a companion galaxy, and you can see it comes out of this arm here. The point is that this is probably an ejection in the disk of the galaxy, and I will argue later that the spiral arms are formed by these ejections. And this is a nice tie-in with the plasma theories that we've been talking about here. Since they're moving in the arms, they're slowed down a little. They develop earlier. And this is a companion galaxy just making the transition. Here, this is plus 5,000 kilometers per second higher redshift. And everybody said this was obviously a companion. And then they found out what the redshift was. And they said, no, it must be an accidental configuration, even though you could trace it back here and see where it came out of the arm and sort of the slot in here. Now, this is a particularly beautiful photograph. I think it was voted the most beautiful photograph of 19-something or other. It's from the VLT, the new European Space Organization, ESO, 8-meter on power now. And this picture is pasted on the bulletin boards and the walls of all the major observatories in the world, and everybody looks at this and they don't notice this galaxy, and they don't notice this galaxy. I talked to one of my friends who was responsible for posting this around. I said, you know the story on this? And he said, yes, yes, I know, but we don't want to talk about that. This is one of the Atlas of peculiar galaxies known as ARP 105. And here you see a beautiful example of ejection. Here's this ejection coming down this way. It's called Ambar-Tsumion's knot, and it's obviously a galaxy in the making. Here's a quasar redshift 2.2 over here. The ejection has obviously gone off in the other direction also and punctured this galaxy and formed this big plasma loop out in here. So this is sort of an example a physical example of what happens when you can see these ejecta where they intersect other material and what they're like. There's a whole lot of companion galaxies in this area, and the next slide shows that they're systematically redshifted. And you see this is at 8,500 kilometers per second, and they go up to 8,900 kilometers per second. Every one of these companions is redshifted. And this is another terrible controversy that's been going on for years and years. And the conventional astronomers say, no, that this is just an accident, because if these are really velocities, of course, you should have as many coming towards you as going away from you. And in fact, they're all positive, which means that there's an intrinsic component in there. And even though I've been saying for years that if you look in our local group and the M81 group, that 22 out of 22 of the companions are all positively redshifted, people will still say, well, it's not a big enough sample, or maybe an accident, and so on and so on. But it's very important in this story, because this is where the younger galaxies wind up. This is a more recent, quite recent picture of the jet in M87, and this is taken with the VLA in Socorro, New Mexico, the radio telescope, the biggest radio telescope we have now. And here's this famous jet coming out of the center of M87, and I'll show you what else is going on in M87. I mean, we could spend the whole afternoon talking about the Virgo cluster. Amy showed you some of it. The center of the Virgo cluster is down here. But I just put this in here to as an excuse to make the following comment. The conventional picture is that these are plasmoids shot out from the, I'm sorry, that this is an ejection of material coming out, and that these are shock fronts. There are shock waves out in here. And they are going with 0.99 the velocity of light. On the Hubble Space Telescope, you can actually see them move from year to year. And if, under the current theories, you make them move that fast, you have to pump a tremendous amount of energy into them. And if you pump that much energy into a normal plasma, it's just going to dissipate. It's just going to blow apart. But we have to, because there's a string of galaxies along here, and because there's a quasar out here, and because there's another cluster out here, and so forth and so on, we have to get these things to evolve into, condense into quasars, and then evolve into galaxies. And the thing that I will talk about is, if these are new matter in creation coming out with zero mass or near zero mass, they'll be moving initially with the speed of light, and then as they gain mass by communicating with the rest of the universe, we'll talk about this in a minute, in order to conserve momentum, they have to slow down, as we've seen from the ejected pairs. They have to slow down. They gain mass. That's going to reduce their kinetic energy. It's going to reduce their temperature. And instead of blowing apart, they'll be able to condense into new galaxies. And I think this is a very, very important conclusion to draw from all these observations, which I'm showing you. Another view of the Virgo cluster is in the X-rays. And this is taken with ROSAT, this German X-ray telescope, of which I now have access to the archive results. And this, being a very important cluster, of course, was observed in the X-rays. And the NPE people sent this paper to Nature. And of course, it was published immediately. But I noticed that this was leading right down toward the center of the Virgo cluster here, M49. And then it was leading on down to 3C273, which is one of the first discovered quasars, one of the brightest quasars, and one of the arguments was that, original arguments was that you wouldn't find the brightest, by accident, find the brightest quasar in front of the brightest cluster and then have it aligned directly across the center galaxy. However, you can see now this, again, this material connection from low redshift galaxies into this quasar, and this is a bona fide quasar. So I had this very clever plan. I said, well, okay, when nature publishes this picture, this one that I reduced with the same observations and the same reduction procedure, if they publish this, they're going to have to publish this. So as soon as this appeared, I sent this in, and of course it was turned down. But so it was eventually published in Physics Letters A, I think, or something like that. The next slide shows that not only is the Virgo cluster filled with X-rays, which are very high energy radiation, say kilovolt or something like that, but here's the observations with gamma ray telescope. Now this is a very expensive satellite telescope that was sent up called EGRET, and these observations in gamma rays with huge energy, about 100 to 1,000 MeVs, showed that here's M87, here's the center of the Virgo cluster, M49, here's 3C273 at a redshift of 1.62, I think, and it's connected in gamma rays. And not only that, it's connected down here to 3C279, which is another big quasar at a redshift about 0.553. So this whole thing is connected together by gamma rays. And I thought this was really a sensational discovery. The young worker in the gamma rays who did this and who brought it to me to help with the publication and so forth, was finally able to publish this result after tremendous opposition. But he now went out of the field and has become a science writer. There was no place for him in this field, even though I thought he was one of the best prospects, best young workers there were. There was no place for him in this field after he published this. But it's an extremely important observational result. Now I want to summarize temporarily and a sort of interim summary of what we've learned from this sample of observations which I've shown you. Here's a parent galaxy, more or less along the minor axis. You start out with a quasar at redshift 2. As time goes on, it goes out, it slows down, it becomes z equal 1, z equals 6/10, 3/10, etc. And then it starts developing into a compact galaxy, and the companion galaxies that wind up here at about 150 kilometers per second, 100, 200 kilometers per second excess redshift. You can also look in the other direction. They develop at this rate. It's the same in both ways, but they develop into X-ray QSOs here, and then into this BLX stage where they're very energetic and the spectrum washes out, and they start secondary ejection, and you get multiple galaxies. And this is very important at the end, where I'll show you about galaxy clusters. This is a galaxy 3628, which is ejecting plumes of hydrogen. And some innocent conventional astronomer didn't see it there and was measuring quasars, and he measured all these quasars around it. When I noticed that this plume was coming out, being ejected, and also the X-ray observations showed that the ejection was coming out along this minor axis. And the people who published this actually said that the X-rays are being ejected along this axis, and I could see these quasars here. I made a special effort, now this time with an amateur in New Zealand who was actually the one who first pointed this out to me. And you see on the next transparency, you see in X-rays now, here's the center of 3628, this very active nucleus, and here are the X-rays that they're talking about, which are being ejected along the minor axis. And lo and behold, here's this quasar, a redshift 2.15, which is really high for a quasar. And it's right on the edge of this ejected filament. There's also a X-ray source up here with Margaret Burbage got the redshift of. It's a quasar. And of course, when we went to publish this, it was turned out flat. And it still hadn't been published. And I might say that we're making a sort of end run around this, and more pictures are being taken. And also the new Chandra X-ray telescope, I happen to know, is got this program to take X-ray and with higher resolution and higher sensitivity. And when that becomes available in the archives, it's going to be public property about 6 months after it's observed, then we'll be able to get a better, an even better, although I don't know why we need a better connection than this, but we'll be able to do it anyway. Maybe we get a chance of getting it published. This is a recent triumph. I say, you know, things get very discouraging sometimes, and then something happens and you suddenly get very enthusiastic and very excited. And this is supposed to be one of the most luminous galaxies in the universe because it was taken from my atlas. And when they measured in the infrared, it was very bright in the infrared. And at its redshift distance, it's supposed to be an ultraluminous infrared galaxy. But I never believed that it was at its redshift distance. I always felt it was much closer. So I didn't want to object to the fame which this object has achieved, but I really don't believe that it's that luminous. Now, taking the recent observations on this is shown here. Here's the hydrogen map, which I had to beg hard to get, but I finally got permission to use this. Here's the hydrogen map showing it goes from ARC 220, which is about 0.018 redshift, down to these galaxies, which are a 10th redshift. And it was another case where the people said, oh, these galaxies are connected back. And then they found out the redshift was so much higher. And then they said, oh, well, it must be an accident. I got a hold of the X-ray observations from this. Again, these were in the archive. And I show the next slide. And that was really exciting because here's the central galaxy, ARC 220, at 0.018. Here's these galaxies, and they're connected in the X-rays as well as the radio. And then you see this line of X-ray spots leading down here to a blue stellar object, which is an X-ray source, and up here to a red stellar object. Most of the time these quasars are blue, but sometimes, occasionally, they're red. They're hard to pick out and hard to find, and they're probably obscured by dust. But so the question was, could we confirm these two as quasars? And in this last June, I think June 2nd and 3rd, I was observing with Margaret Burbidge on the Lick telescope at Mount Hamilton, and we had only a 2-hour slot to try to get this, and the lights of San Jose were very bright, and these objects were very faint, but we went after them anyway. We went after this one because it was so difficult and red, and when the exposure was over and it came up on the screen, we saw, lo and behold, this beautiful emission line. So it meant it was a quasar. And that was a great uplifting event. And we immediately said, okay, let's take the last 50 minutes and go down on this, which is even fainter. And we got the spectrum of that. And it had an emission line in the same place, which means that the redshifts are the same. So we have this beautiful pair across this active galaxy, connected in by the X-rays and having similar redshifts. And that is in the process of attempting to be published, but it's a lot of fun. Now, Amy showed a picture of M82, and M82 is well known for, it's a nearby companion to M81, of really blowing its guts out. I mean, it's just coming apart here, and it's blown a cap off here and so forth. And as Amy mentioned, there's a bunch of quasars down here, which everybody tries to ignore because they're very high redshift. And they obviously come from a part of this explosion. So the next slide shows, again, going to the archives now, which are very accessible now by internet. And you see all these quasars of high redshift down in here. And these X's are X-ray sources. And obviously there's a string of X-ray sources going out this way and going out this way, almost along the line of ejection here. And it's the same old story of these things as soon as you measure them, if you can get the telescope time, to measure them, and they'll turn out to be quasars also. So the next slide shows the most recent observations that I could pilfer from the archives. And this particular astronomer had numbered all these point sources as X-rays. And of course the X-ray people, the conventional people, say that this galaxy is blowing out X-ray material. But there were all these obvious point sources, which, as you and I know, are quasars. So I said, okay, would you give me the positions of these objects so we can observe them, get the redshifts? And he wrote back and said, well, no, we threw away these positions because they were background objects. And so I can't give them to you. So I measured the positions anyway, and we'll go ahead. And we're in the process of working on that. Now, we're getting serious here because this is another radio galaxy, and the radio mission is shown in green. It's done by a friend of mine, Alan Stockton, at the University of Hawaii. And this quasar, this radio galaxy is about a redshift of a tenth. Well, there's a tenth difference here. And so the radio material is in green, and the optical material is in yellow. And you see what's happened is that this ejection has taken place, but the radio plasma, being light and interactive with the intergalactic medium, has been stripped. And the optical, more dense part of it has gone on beyond it, but it still retains the same shape. And the same thing has happened down here. The optical material, being denser, has gone on, and the radio material is being stripped. This explains a lot about a lot of the observations that we see. The interesting thing here is that this turned out to have a different redshift by a tenth than this, and so my friend Alan concluded that this is an accidental background object and had nothing to do with it. But I think it's beginning to show us what's happening with the plasma component of these ejected quasars. Let's go ahead. This is the latest thing, and I think this is extremely exciting. This has to do with galaxy clusters. I said in Seeing Red that it looked like the galaxy clusters were associated with nearby galaxies. And this was really the worst heresy that I could have imaginably said, because everybody, even including my closest friends, said, "Chip, that's crazy. You can't do that. You're going to really, you're going to ruin the whole thing." But nevertheless, with the assistance of an amateur high school teacher in northern New York State, we put this paper together. And here are two clusters. They're indicated here and here. They're very populous galaxy clusters. And they're at a redshift of about 17,000 kilometers per second. And they both have the same redshift. And they form this pair. And so we know where to look when we find a pair. We look in the center. And lo and behold, here's an active galaxy with a redshift of 5,000 kilometers per second. So it's the low redshift galaxy, which is a host to these. And what I plotted here is the circles of the 17,000 kilometers per second redshifts and the pluses of the 5,000 kilometers per second redshift. And you can see that they're intermingled. So they can't be at different distances in the universe. They must be at the distance of this nearby cluster in the center. And you can see them actually intermingled along this line. Now, the really thing that was exciting, because just 2 weeks ago, it appeared on the Internet preprint server that they'd taken this in Chandra, the new high-powered X-ray telescope. They'd taken it with Chandra, and because it's pouring out a huge amount of X-rays, and they've identified what they call a bow shock here, and they concluded that this whole thing is moving out with 1,400 kilometers per second along a line which is exactly back to what we said was the origin. So this, I think, is the newest revolutionary step, and that is it's implying that as these quasars come out and they break up, they can break up into a whole cluster of galaxies, something that people have always said were out at the edges of the universe along with the quasars and so forth. The next slide, I think, shows the center. No, it shows another example. In this paper that's submitted now, and by some miracle, I think it's going to be published. There's another example of these are Atlas objects, 470, 474. Pair of quasars across here. The chance of these bright quasars, they're both 3C quasars, is about 1 in 10 to the 9th, 1 in a billion of being accidental. And then these are Abell clusters. And you can see how their redshifts match again, 0.049, 0.046, 070, 0.067. So this, we've shown about 20 examples of this now. The next slide shows a sort of it's not a random picture. These are high redshift quasars, and there are about 4 of them together. And the favorite explanation for this is that it's gravitational lensing. And they want to have them gravitational lensed by this foreground cluster here. But they never seem to notice that this foreground cluster extends right back down the line to this big bright galaxy here. So this is just sort of a random example of the connection of these high redshift objects to the low redshift objects involving the clusters, which nobody can see, except if you look at it this way. This is a newest one of these clusters of galaxies. It gives you a good idea what these clusters will look like. They're very faint objects, and these are isophotes of X-rays. So this appeared also in the ESO messenger, and when you see this definite elongation of this cluster this way, immediately we would ask, what's up here? And exactly 14 arc minutes away is this big galaxy, NGC 720, with an X-ray filament coming out and curving down along in this direction. So this seems to be sort of, a breakthrough, and this is just happening right now. I think we're about ready for the theory part of it. And as I say, everybody's going to have their own theory, but I want to just follow through the implications of what we've been doing so far. The conventional theory. The conventional theory is the Einstein field equations of general relativity. And really, it's much more simple than it's advertised to be. This T mu nu is just the kinetic energy and the potential energy and the momentum terms, all the dynamical terms. And these are all geometrical terms, Riemannian tensor, so forth. The solution made in 1922 made an approximation which I think was wrong. It just assumed that the whole universe was just like our universe and that the particle masses were constant everywhere in the universe, that the electrons always had the same mass, the protons always had the same mass. And they then solved this equation with this approximation, and they got that the space, this is the scale factor of space, varied as the redshift. And so this is the expanding redshift solution. This is the Big Bang solution. And they predict expanding coordinates, singularities at time equals 0, and it demands that all the redshifts are velocities of recession. But now we've seen that runs up against the brick wall of the fact that they're not velocities of recessions, they're intrinsic. So what I'm saying is that this whole approach has to be abandoned. This whole approach has to be abandoned. Well, it creates this terrible sense of panic in most people, because what are you going to substitute in its place? Luckily, in this case, Jan Narlikar, who's a student of Fred Hoyle, and Hoyle and Narlikar had investigated the general solution of this equation, which was not to assume that particle masses were constant with time in the universe. And in that case, they got a very simple solution, that the masses varied as the time squared, i.e., in the beginning, when they were first created, they were 0 masses, and as the time went on, they communicated with more and more of the universe, and their mass grew. This is a Machian theory. And so if the electron mass, when it makes its transition in the atom and emits the photon, if the mass is small, the photon is weak, and it's redshifted. As the electron grows in mass, the photon which is emitted is stronger, and it drops in redshift. So this is a perfect explanation for what we've been seeing, that the younger objects are high redshift. And the Hubble constant, the sacred Hubble constant, is just the inverse age of our galaxy. And there's a lot of things you can say about this. It makes a link between quantum and classical mechanics, because the creation of the matter is in very small particles in the quantum regime. There's no more singularities. the creation points are at m equals 0. And the most important point, and this is something I want to stress for just a minute or so, is that this is in flat space-time, Euclidean space-time. In other words, you don't need any of these complicated curved space-time coordinates. And in fact, I would argue that the conventional solution needed these to account for the incorrect treatment of the mass particles. So that if this is a general solution and applies throughout the whole universe, and you get a simple solution, and you don't need these curved space-time coordinates. Well, if you don't need the curved space-time coordinates, then what are you going to do about gravity? This took me a little while to sink in, but I finally faced this, and it's caused me to seriously consider something Tom Van Flanders has been working on, a number of people have been working on this question of Lagrangian pushing gravity. And I made up the following transparency to illustrate what's sort of going on here. And that is in this variable mass theory, which we need to explain the redshifts of the quasars, and also they're starting out with low luminosities and evolving. We do have a primary reference frame. In the relativistic solution, a primary reference frame is forbidden. And yet, the common sense would tell you that if you just average over the universe that you detect, that's your reference frame. So again, I borrowed from Tom Van Flanderen on a number of these common sense arguments here. There's another movement here which has been started by some other independent thinkers who I think are thinking very well, that if you take the two time scales which are necessary for our solution, the Narlicker-Arp solution, you have a universal time and a time for our own galaxy, for our own clocks. And our own galaxy is born with the clocks running slow, and as time goes on, the clocks speed up, approach universal time. So if you take these two time scale approach, then you can solve all the normal triumphs of the general relativistic equations, perihelion and Mercury, and so forth and so on. And it all works out very well. And here are some of the names associated with this alternative approach to the general relativistic approach. So without going into any more detail, I would say that it looks like the observations of the quasars are requiring a more general and a more simple solution to the physical dynamical equations, replacing the general relativistic approach and accounting for all these phenomena, both locally and cosmologically. And it requires, even though the mathematics may be quite the same because it's just a conformal transformation between them, the physical picture is completely different. Instead of having a universe that was all born at one instant 15 billion years ago out of nothing, you have a universe that's indefinitely old. It's not expanding. The Big Bang is forby, is gone, passé. And you have continuous creation of new galaxies within this, well, it's kind of a real steady-state universe. And it relies on the fact that we live in a hierarchical universe. And this is kind of interesting, because if you start in the galaxy nucleus, you get a high density. These are all just rough estimates on my part. In the center of this active nucleus, this mysterious engine where the stuff is created, and we can maybe talk about that informally, that density is very high. So the new particles are in that environment, and they're gaining mass from their environment very rapidly. When they step out of the nucleus, they go into a different, much lower density environment, into the bulbs of the galaxy. And then if they come out in the plane, they go out here. If they come out along the axis, they drop down here. These are enormous drops in density from 5 in the log or something like that. And then finally, when they break out of the local group, they take another stop down, and out of the local supercluster, they take another drop down. This means that these particle masses will be gaining mass very rapidly, and the redshift will be dropping very rapidly on one of these steps, and then it levels off, and then it goes to another step, and it drops. And there are just about 1, 2, 3, 4, 5, 6 drops, and there are 6 major quantization levels. So what we're suggesting is that maybe this redshift quantization that we're seeing in the quasars is a reflection of the density hierarchy in the whole universe. And of course, it's an unbounded universe. We don't know what's going on out there. Okay, one final pretty picture. This is NGC 1097. This is a whole run I had on the 4-meter telescope in Cerro Tololo, and we got these beautiful jets coming out here, and everybody admits that they're extremely mysterious, and nobody knows what they are, but they managed to stay away from investigating them. But because of a friend who does have access to the big telescopes now, we're now starting a project where we're going to observe this object and some of the ones in here. And this is really kind of a discovery astronomy, and that is, this might turn out to be a pure Bremsstrahlung, featureless spectrum, synchrotron emission, plasma, a young galaxy that hadn't even formed atoms yet, or it might turn out to have a huge redshift, 4 or 5, and then it would be a spectacular confirmation. I don't know. The observations are about a month away from being done. We'll have to see. Oh, there's one more thing I want to show. Yeah, it's that crummy drawing that I made. Because this finally I've come to something that really pertains to what this conference is about, and I want to just point out and provoke people and so forth, and say that what I think is happening here is that you have a galaxy and an active nucleus, and it throws out one of these low mass plasmas, which is the quasar, in the beginning of the quasar, and there's some sort of magnetic field in the center of this galaxy, or in the center of the nucleus. It's probably tangled. You don't care what the form of that is, because when it's stretched out, the magnetic field lines are stretched out this way. Now, this quasar obviously breaks out of this magnetic cocoon, or whatever it is, and at that stage, I would think that it's a plasma, but not a net charge. In other words, you've just vaporized the material, or you're going in the opposite direction, so that the pluses and minus equal, so there's no net charge. However, they're swinging around and emitting all this X-ray and Bremsstrahlung and so forth. As time goes on and they cool, the electrons go into orbit around the protons. That's not a smiling face. That's supposed to be a primeval hydrogen atom. And it's beginning to form atoms and molecules and stars, and this is the progression into a companion, into a new galaxy. And here, I want to emphasize this, because I think this is of interest to this group. There is something known about the magnetic fields in galaxies, and for instance, the Japanese astronomer Sofue and some others have done polarization work in the spiral arms, and they find that the magnetic field lines run out this way and then back this way, in one direction on the outside and the other direction on the inside. And what I think is happening is that these same ejections that are coming out as quasars along the minor axis come out in the disk of the galaxy, and they drag the material out with it, and they form these sort of flux tubes in which there's some material, ionized material of the galaxy, which then is constrained, or maybe even there's pinch activity, and they form these characteristic young stars along the galaxy spiral arms. And so what I'm trying to say is, I think there's a unified phenomenon here of ejection from these nuclei, forming quasars, new galaxies out this way, and pulling out material of the old galaxy, forming these new stars and so forth. And that I would suggest this as a sort of a mechanism for understanding galaxies, evolution of galaxies, birth of galaxies, and so forth. So there it is. I thank you.